We'll turn to tonight's lecture on improving the tick-tock of the atomic clock. And it's my pleasure to introduce tonight's speaker, Andrew Ludlow. Andrew is a physicist and project leader in the Time and Frequency Division of the National Institute of Standards and Technology in Boulder, Colorado. He currently leads research and development of the ytterbium optical lattice clock at NIST. His research activities include the development of optical atomic clocks, cold atom systems, quantum metrology, ultra-stable optical sources, and laser interferometry. He's been an author on many scientific publications on atomic clocks. He was awarded the DAMOP Thesis Prize of the Atomic, Molecular, and Optical Physics Division of the American Physical Society for his doctoral work. And he is the recipient of the Young Scientist Award of the European Frequency and Time Forum, of the Rocky Mountain Eagle Award for Scientific Achievement, and the Department of Commerce Gold Medal. He earned a BS in Physics from Brigham Young University and a PhD in Physics from the University of Colorado, working at Gila Institute of Physical Sciences, formerly the Joint Institute of Laboratory Astrophysics, which is run jointly by University of Colorado and NIST. After completing his doctoral work at UColorado, he was a National Research Council postdoctoral fellow at NIST, where he has since become a research physicist and project leader. His talk tonight is on improving the tick-tock of the atomic clock, telling time to an accuracy of 1 second in the lifetime of the universe. Please hold questions to the end and join me in welcoming Andrew to the podium.
All right. Well, it's great to be here with you. It's a real pleasure. Being from Colorado, I don't make it to these meetings very much, as it turns out, so it's particularly special for me to be here with you tonight. So, as Larry mentioned tonight, I want to tell a little bit about some of our work as we try to push the limits of timekeeping and really exploit what these wonderful timekeepers, these atomic clocks, are capable of doing, and why that's interesting to us. It was quite interesting to hear some of the minutes from the last lecture by Bill Phillips. His name will come up once or twice in some of the foundational research that really makes possible some of the work that's going on here. So it builds off quite nicely, and I hope that'll be a strength that I can build off that discussion from last time. So before I get going too much, I just want to start with a quick comment just on kind of choice of wording. In case I slip in and out of different language, sometimes in our community, we'll call a clock a lot of different things. It could be a clock, it could be a frequency standard, it could be an oscillator. And there are some differences between those, but for the purposes of discussion this evening, if you hear me use any of those words, what I mean is what we would nominally call a clock. Okay, so I thought I'd start in a real simple place with a wristwatch. In fact, this is my wristwatch. It's the one I wear all the time. I'll be the first to admit that there's nothing too special about this. I got it for $20 on Amazon. But despite that, it services me pretty well. It does a decent job of keeping time. It's got a chronometer. It's got a countdown timer. Pretty useful. But I will admit that it's not perfect. It runs a little bit fast. And I know this. I'm regularly reminded of this because every day when I come into the lab at NIST, on the doorways, there are some wall clocks that are mounted right above the door. And these have little radio receivers. You can see a little insignia there where it's synced up to a radio broadcast signal that NIST itself transmits and actually propagates across the entire continental United States. And that radio signal itself is linked to some atomic clocks that NIST maintains. And then the idea is that this clock here, receiving that radio signal, is able to synchronize ultimately to the atomic clock so that we don't need to go in there and adjust time when it gets off. And I took these pictures just the other day, a few seconds apart, and you can see that the real time's about 4:56, but my watch says it's about a minute after that, 4:57. I'm even more regularly reminded that it's not a perfect clock when I look down at my cell phone. These are actually pretty good indicators of time, even though the oscillator or the clock inside our cell phone is pretty cheap and not that good. But because it's linked with a cell phone network, it actually synchronizes over the network, and it is pretty decent. So this communication with the cell tower, these cell towers have their own clock. Sometimes, and most commonly, it's some type of clock which isn't very good, but it's itself linked to a GPS satellite, which has atomic clocks on board. And so that makes it quite respectable. And in some cases, they actually put true, real atomic clocks maybe in the little substations by the tower. And this turns out to be very important for the operation of the cell phone network. But kind of as a freebie, it means that we can get pretty good time on our cell phone. So all of this kind of is maybe a good introduction to the idea that we can use good timekeeping for a lot of things that don't, on first glance, have much to do with keeping time. And perhaps the most well-known or famous example of this is GPS. In this network of satellites, there are a whole bunch of atomic clocks. Each satellite has several different atomic clocks. And a person on the ground with a local receiver will receive satellite signals from a number of satellites. Each one of those signals indicates the time it was when the satellite transmitted the signal. Because the satellites are at different locations to each user, the handheld receiver receives those signals at different times, and those time differences are noted. And that is what's fundamentally used to triangulate the position of where you are based upon how long it takes those signals to transfer down to you. And so really good clocks can now be leveraged in order to provide good navigation, much like I gather that Dr. Phillips talked about at the last lecture. This kind of thing is also exploited in communication systems and advanced networks. They're needed in order for these systems to run well. A good example, someone I was talking to recently was talking about the new 5G networks for cell phones, that in order for them to work properly, they need to have of order microsecond accuracy in their performance. And at the point where they lose that type of synchronization, phone calls start getting dropped. And so you need a good timekeeper distributed throughout this network in order for that system to reliably operate. Another place that these atomic clocks or good precision timekeepers are used is sometimes in radio telescopes, something often called very long baseline interferometry, where you might see an array of radio telescopes, and in some cases this array might extend beyond what you can locally see and could include facilities throughout the world. And basically they receive signals that are time dependent, and by basically linking up signals from different receivers that are located all around the world, if they can link them up in a coherent fashion using very, very careful time tags, then they're able to effectively take an image which has a resolution of a telescope as far apart as the telescopes themselves are. So it's this synthetic aperture. And so that increases the resolution quite a bit, but it absolutely requires that there be a well-characterized time between these remote facilities. So often these places will have actually a pretty fancy atomic clock on site. And then there's also a number of high-performance synchronization situations, like some accelerometer applications where you're working with a very limited window of time when you need two things to arrive at the same place for a certain measurement. So you need a really good clock there. Well, for the most part, the type of oscillators or clocks that are providing this timekeeping are shown here. And as you might imagine, most of these things are commercially available. And they're pretty darn good timekeepers. So a good example is an atomic clock based upon rubidium. They make these things in all different kinds of varieties. In fact, here is shown a little CSAC, a chip scale atomic clock that it was developed in the last decade that's quite small. And these things can keep time pretty darn good. Just a range of values might be at a part in 10 to the 10, so a part in 10 billion, or even a couple orders of magnitude higher in some cases. There's also a lot of applications where you can use kind of a not-so-good clock, but like I mentioned in some telecom applications where it's just disciplined through GPS such that it behaves like a much better clock. It inherits the characteristics of some of the GPS atomic clocks. So this is quite useful and very cost-effective. For more demanding applications, you can get what's known as a cesium beam clock. These are also commercially available in many cases. This is actually kind of one that's been around for decades, and it's kind of a workhorse for some high accuracy experiments. You pay a good price. Something like this might cost between $50,000 and $100,000 or so, but has an accuracy of at least 1 part in 10 to the 12, and sometimes better than that. So it's quite good. And then for even more demanding applications, there's a clock that's been around for many decades, the hydrogen maser. There have been Nobel Prizes awarded related to its invention. And like these very long baseline interferometry places, we'll have one of these on site. And that one will cost you a good fraction of $1 million, but you get higher performance in terms of the precision it offers, maybe even an order of magnitude beyond some of these other ones. Okay, so these are the guys doing the hard work for the most part. This is what's actually providing the timekeeping. Now, because time can be measured so well, and because atomic clocks are the best way to measure time, it turns out that atomic clocks are the natural choice to even define what time is. So in the international system of units, the unit of second is defined here, and this is a quotation directly from the international treaty which recognizes this unit system. It's the duration of approximately 9 billion periods of radiation corresponding to the transition between the two hyperfine levels of the ground state of cesium-133 atom. So basically, this just means that when you excite a cesium atom from its ground state up to this other hyperfine state, it oscillates, and if you count about 9 billion of those oscillations, that's a second. So this is, in fact, the definition. Because time can be measured so well, it's, in fact, the best physical quantity that we can measure in terms of precision. Other physical quantities are often also measured by leveraging our ability to measure time or its inverse frequency. And you can use that precision to try to measure these other physical quantities well, better than you could otherwise. And a good example of that is the internationally accepted unit of length is measured in terms of our measurement of time. So here again, also from the international treaty, the meter is the length of the path traveled by light in vacuum during a time interval of this fraction of a second. So you just watch light, and when you count that amount of time, which an atomic clock can do that, then that's a meter. There's also other applications where this comes into play. So actually, one of the most practical references for the volt is, as shown here, an array of Josephson junctions that basically give you a conversion from voltage to frequency. And so if you have a tool to measure frequency really well, and that's what atomic clocks or frequency standards are good at, I'll again use time and frequency almost interchangeably. They're just the inverse of each other. So you can leverage the power of an atomic clock to actually, with one of these, now have a very good standard of voltage. And more recently, there have been proposals to actually measure temperature by leveraging our ability to measure frequency well. This is basically measuring the frequency spectrum of different atomic systems. And the width of that spectrum is related to the temperature of the atoms. And then there have even been more recently some proposals trying to relate our measurement of mass back to the measurement of time. Okay, so the atomic clocks can do a lot of neat stuff. That really begs the question is, why would I want an even better atomic clock? What's the point? And obviously for you and me in our normal everyday lives, there isn't much of a point. What we've got now is pretty fantastic. But believe it or not, there's a number of very interesting scientific and technological applications that, continuing in the same spirit of trying to leverage the ability to measure time very well for some other applications, that atomic clocks can actually provide some very useful insight into even the universe around us. So one of the most well-known examples that atomic clocks have already contributed to science, and that they can do so much better with these new generations of clocks that are being developed, that I'll tell you more about here in a minute, is in order to test general relativity. In particular, to test it with the idea of maybe testing it against competing gravitational theories. So basically this all goes down to one thing, and this is the so-called gravitational redshift. One of the most straightforward predictions from Einstein's theory of relativity is that if I have a clock and I'm sitting in a gravitational field, it is going to naturally tick slower than it would if I compared it to a clock which is outside the gravitational field. That's just the way space-time works in a gravitational environment. So it ticks slower. This is known as the gravitational redshift. And we have observed this phenomenon. It's not a huge thing. On the human experience scale, we don't see this effect. But it is there, and atomic clocks actually regularly have to take this into account. When I compare an atomic clock in Boulder, Colorado, where I'm from with one that's, say, on the coast down at sea level, I have to take into account this effect, otherwise there would be an egregious error in the timekeeping compared to what atomic clocks are capable. So this is a non-trivial influence. Well, it turns out that there's a lot of folks that think that GR is not the right gravitational theory. It's not completely consistent. It hasn't been able to be unified with the other forces of nature, and that there's something more out there that's going to replace it eventually. So alternative gravitational theories exist, and they also predict a gravitational redshift, but they disagree with Einstein on what the value of that shift is. They think there are some higher order corrections that Einstein has missed. And so if we can precisely measure this effect, we can discern whether or not Einstein continues to be right. Right now, the most careful measurement of this effect was done by taking one of those fancy hydrogen masers. I've just kind of taken the top of this paper from 1980. They took one of those hydrogen masers and they launched it up into space and watched it come back down. And through the changing gravitational environment, they were able to measure this effect. And Einstein got it right at the 70 part per million level. So at the best that we've been able to measure, Einstein's right. But there are those that would disagree with that. And so as these new clocks become more and more capable, we have the potential to measure this more than 1,000 times more carefully than what has been done in the past, and really understand if Einstein has been right all along. There's also an opportunity to test fundamental tenets of relativity, like local position invariance, which basically says this gravitational redshift, it shouldn't change where we are in the universe if the gravitational field doesn't change, and it shouldn't change whether I'm talking about an atomic clock based on one atom or another atom. It's all the same thing. And so we have the ability to test that out. Another actually technological application of this effect, the gravitational redshift, is actually in geodesy. And the phenomenon is becoming known as relativistic geodesy, or sometimes the term chronometric leveling is used. Basically, the idea is as these clocks become so good, previously we thought of the gravitational redshift as something to worry about, to add a correction to make sure that we didn't mess up our timekeeping. But now they're becoming so good that we're thinking them instead of as gravitational sensors. Can we use these clocks to actually measure the gravitational potential of, for example, different places on the Earth? And it turns out that the capability that the new generation of clocks brings compares favorably with existing technology, state-of-the-art technology in the geodetic community. In particular, they have issues where, for example, they'll have measurements of vertical height and the gravitational potential of a certain reference marker that then gets extended, that gets measured across, let's say, a country or a continent. And the techniques for extending that across the country can introduce error in the measurement. Many countries maintain their own system of vertical markers, and there's discrepancies between those areas. And that's because to extrapolate over long distance scales, it introduces error. And so an atomic clock operating at, let's say, 1 part in 10 to the 17 or 10 to the 18 accuracy, as I'll show you we're now starting to do, means that you can actually sense the change in the gravitational potential corresponding to just about a centimeter in height change. And so these clocks are now becoming very good probes of the Earth's gravitational field. And so you could, in principle, help characterize what is shown here, the geoid, which is the gravitational potential surface for the Earth corrected towards sea level. Such a thing has been demonstrated roughly, actually at NIST in Boulder, where some collaborators took 2 atomic clocks that were sitting right next to each other, and these are very good atomic clocks, and then they raised one up about 1 meter. And if you have a part in 10 to the 16 accuracy or precision, then you can sense that, and that's what is showing, like, oh, they just raised it up, and that's a gravitational redshift. So that's corresponding to 1 meter, and that was a pretty big deal because nothing like that had been observed directly. Usually when we observe it, it's over distances of many kilometers. But in this case, it was quite small, and right now we think we could maybe do even 100 times better. Okay, another reason why this is interesting is there are also theories out there, a lot of string theories, for example, that actually expect that what we call fundamental constants of nature, the things that we might learn in a high school or college physics class that says that thing, oh yeah, it has this value and it never changes and that's the way it is, they actually predict that these fundamental constants of nature actually change. And there's some complicated reasons for why they predict that. I don't even understand all the details, but ultimately they do predict that it's required for things like conservation of energy, sometimes when they have multiple dimensions and so forth. The only way that energy can be conserved is when these fundamental constants actually have some variation. And so it turns out that atomic clocks are really good at measuring this. And why is that? It's because the reason that the atomic clocks tick at the rate that they do is it all comes down to how the electron binds to the nucleus. And the energy and the way that it binds to the nucleus is a function of these fundamental constants of nature, like what's the charge of an electron, what is the speed of light, these kind of constants. And so if these fundamental constants of nature are actually changing, that means that atomic clock ticking rate is also changing. And so we could measure these things over periods of weeks, months, years, and eventually decades, and try to observe whether or not their ticking rate is changing. Typically, we have to do this by comparing different types of atomic clocks. If you have the 2 of the same variety, let's say based upon cesium, they could be changing, but the problem is they'll be changing at the same rate, and so when you compare the 2, you won't realize that they're changing. So you need to compare different types of atoms, which exhibit different sensitivities to this potential variation of the fundamental constants. And then you can sense that. And that's what this graph is showing here. I don't want you to get too much from this, just to say that some of the most important fundamental constants that we talk about, the fine structure constant and the ratio of the proton to electron mass, they're shown here as alpha and mu respectively. And this is a graph of their potential variation. These clocks are sensitive to variation of both, so it's sometimes difficult to constrain, well, which one would have been changing. But by using different species of atomic clocks, you can kind of orthogonalize the problem, and that's kind of what you're shown here in green and purple. And at the end, there's this white ellipsoid of uncertainty, which says, we know that they're not changing outside this bound, and significantly you can see it kind of overlaps with 0. So to the best of our knowledge, these measurements indicate that it's not changing. Now, this is an interesting thing in its own right. An alternative approach to trying to use atomic clocks to measure this effect is instead to actually look back in time hundreds of millions or billions of years using celestial observations, where you can look back at a star system. In particular, quasars are most useful for this kind of measurement. They'll look at quasars that are far enough away in the universe that it's effectively looking back, 1 billion years in time. And then they can effectively measure atomic spectra, the frequency that those atoms are emitting out there, and compare it to what the frequency of those atoms emit here on Earth. And if they're different, then a good possible explanation for that is that the fundamental constants were different back then when that light was first emitted. And actually, in 2011, there was an analysis of some cosmic observations that indicated that there might actually be a variation as you look in different parts of the sky. They actually predicted that the fundamental constants of nature vary across space. So this is an interesting area of research that atomic clocks can contribute to. Another interesting place is dark matter. We hear about this sometimes. Right now, the best guess is that, I guess the best measurements indicate that of all the mass energy in the universe, a quarter of it is the so-called dark matter, stuff that we really know nothing about, but that gravitational observations indicate that there's got to be something out there. It exerts a gravitational force on the matter we can see, but we don't really know much about it. To the best of our knowledge, it only interacts with normal matter through gravity, but at some level it must have a weak interaction. And so there are theories out there that try to guess what that weak interaction might be. And then, of course, if it does interact with matter, it will ultimately affect the ticking rate of atomic clocks. So there's proposals out there now that if you could get this global network of clocks across the world, you could actually observe a so-called a topological defect in dark matter, some kind of change in the dark matter distribution that would propagate through the Earth. And it would affect one clock here first, but then the other clocks later. And based upon this kind of transient signal, you would actually be able to detect dark matter and maybe learn something about it. Okay, finally, most of those technological applications that I mentioned could improve as well as the clocks get better. Whether that's navigation, including deep space navigation, that very long baseline interferometry, sometimes those guys ask for clocks better than what the hydrogen masers can give them. Advanced communications, low phase noise microwave sources, radar systems. There's a number of military and defense applications that are either navigation or communication, but that I'm not even fully sure. They don't always talk about that too much. And then, of course, coming from where I do at NIST, where we're thinking about metrology and just measurements, we think about potentially redefining the SI second in terms of changing the definition from Cesian to some improved clock. And then finally, the comment, which goes back a little bit to Bill Phillips' talk last month, which really there's a lot of interesting quantum physics that can be explored with the exquisite control of atomic systems that come with atomic clocks. So there's been a lot of Nobel Prizes in the past that strongly overlap with atomic clock research because of this shared kind of field of interest. Okay, so with all of that, I hope I've convinced some of you that there might be a reason to make a better clock. Now I'd like to tell you a little bit more about how we might go about doing that. And to start, I want to start with the most basic thing, a clock maybe that we're all familiar with seeing. Maybe even some of you have such a clock in your home. It's just an old-fashioned pendulum clock. So if we were to open that guy up, or even just looking at it, we can see that there's two basic ingredients to any clock. The first is it has an oscillator. In this case, it's a pendulum. The oscillator just means it oscillates back and forth. It has some periodic activity, and that is the time base. That is what creates the increments or the ticks of time. And then the second component is it has some mechanism, which is a counter that counts those ticks, those oscillations. And here in the pendulum clock, it's that network of gears together with the clock face that, let's say the second hand is geared to move once a second and the minute hand to its corresponding value. So together, the two ingredients, oscillator and counter, they make a clock. An atomic clock is really no different than that. In this case, the oscillator, it starts off usually as, in a traditional atomic clock, starts off as some electronically generated oscillation, usually in the microwave domain. And then that signal ultimately gets sent somewhere. In this case, I'm just crudely showing that it gets sent over a cable to a microwave horn where it illuminates an atom. And the idea is that atom, it obviously has a number of electrons, including some valence electrons. And those electrons are normally sitting in their ground state, bound to the nucleus. But if we illuminate the atoms with just the right frequency of radiation, something that Max Planck would tell us corresponds to basically the energy interval between these different electronic states. If we do that, we can excite the electron up to an excited state. And only when it's tuned exactly to the right frequency, so that when we multiply that frequency by Planck's constant, do we get to this energy difference. Only at that frequency do we excite the electron. No other frequencies. And so in this way, the atom becomes a useful sensor of frequency. It's only excited when we hit it with the right frequency. So we simply monitor the atom, and we make measurements on it that are basically asking the question, hey, did you get excited by that? And when it does, we know that we're at the right frequency, and then we hold it there. And we keep monitoring that atom, and that allows us to hold the frequency. Otherwise, this oscillator, as the temperature changes, it's going to kind of change around, and that's not very good for a clock. So in a nutshell, that's an atomic clock. So how are we going to make an even better one? Well, probably the simplest thing that we can do is when we're trying to excite that atom, rather than choosing an electronic state that has just a little bit of energy that needs to be excited, let's say, by a microwave pulse, what if we were actually able to excite it to an energy level that was much higher up, something that required optical radiation, light? That corresponds to much higher energy from the standpoint that a higher frequency is higher energy. You just multiply, they're related by Planck's constant. Okay, so by simply going to higher frequency, we can think of it like this. Higher frequency means this wave oscillates much faster in time. And so we are effectively dividing time into finer and finer intervals. I like to think of it like a ruler. If I have a ruler that has increments every inch, or a ruler that has increments every millimeter, the millimeter ruler is going to do a better job to measure the length of a piece of paper, let's say. Same kind of thing here. The ruler in time, if you will, is this oscillating electric field. And something with a higher frequency divides time better. It turns out this optical radiation, this light field, has a much higher frequency than the microwave field. It's much more exaggerated than what I've drawn here. It's about 100,000 or maybe even 1,000,000 times higher frequency. So it really gives us a strong lever arm for dividing down the measurement of time. It gets a little bit tricky now to count the number of oscillations with a light field. With microwaves, we have electronic equipment that can do that. That technology has been around for decades. But a light field oscillates so fast, most electronics don't respond that quickly, so we can't measure that. And I won't talk about this much, but there is a technique. It's actually associated with the 2005 Nobel Prize Physics, the Nobel Prize in Physics, which was this femtosecond pulse frequency comb laser. It's a special laser that basically gives us the way to take a light field in the optical domain and down convert it to a microwave signal that we can then count using conventional electronics. So it's some kind of, let's just for the purposes of tonight, call it this magic black box that allows us to count optical radiation frequency. Okay, so all of that together, tonight I want to talk in particular about one type of next generation optical clock known as the optical lattice clock. And this is the type of clock that I work on at NIST. And in fact, this is the picture of the clock. This is probably the least useful thing I could do at this point, show you a picture of it, because it's not all that illuminating. You look at this and you think, well, this doesn't look like a clock. It's got some kind of weird metal chamber in the middle. It's got a whole bunch of, it turns out these are optics, mirrors, and lenses, and there's some fiber optics. And believe it or not, together this makes a clock. I'll just comment, this is actually a picture which appeared a little bit in some press releases. And this is a caption taken from NPR.org. They say, this may look like a mad scientist's garage sale, but it's actually the most precise clock ever built. So anytime you can insult the clock, take the chance to do it. And it really doesn't look like a clock. Okay, so let's just kind of go through to understand how this works. I just want to start right here. If we zoom in on there, it's what's known as a Knudsen fusion cell, which is basically just a fancy word for an oven. Inside, we heat a particular atom up, in this case, ytterbium. Ytterbium at standard temperature and pressure is just a solid. It looks like a rock of fool's gold, basically. You stick it inside this oven at hundreds of degrees Celsius to make a vapor of it. There's a little hole in the side that vapor shoots out of, kind of like a water vapor in a tea kettle does. And that vapor makes its way down this metal chamber, which is an ultra-high vacuum system. We don't want that ytterbium bouncing into the atmosphere, and so we need to have it in vacuum. From this point on, I'll just use these kind of cartoon pictures to kind of simulate the operation of this clock to help understand how it works. So the atoms are really hot. They're hundreds of degrees Celsius, which means they're moving really quick. And unfortunately, that's not so useful for us, so we need to cool them down. And that's where Bill Phillips comes in. That's one of the places that Bill Phillips comes in. We need to get those atoms cold, and his Nobel Prize was awarded predominantly for the technique of laser cooling. So those atoms are met by these blue laser beams, which basically cools the atoms down from hundreds of degrees Celsius down to, in this case, about 1,000th of a degree Kelvin, so just above absolute zero. This is an actual picture of atoms sitting laser-cooled at a millikelvin. This is ytterbium, this is strontium. At that point, we're doing a lot better because they're a lot colder, but they're still not quite useful enough for us. The reason is this red laser beam right here is what's known as an optical lattice. It's basically just a laser beam that's reflected back on itself. Normally, a laser beam is just a running wave of light. It'll propagate forever, if it doesn't get attenuated by something. But this is actually a standing wave of light because those two running waves run into each other and they create a stationary pattern where there's bright and dark regions of this laser intensity. And eventually, our goal is to trap atoms inside that. But in order to do that, we need to cool the atoms down a lot because if they have enough thermal energy, they'll never get trapped in there. There's just no way that they could get stuck there. Turns out that this laser cooling helps, but it's not enough. So there's a second stage of laser cooling we do that can cool them down to a microkelvin, about a millionth of a degree above absolute zero. And at that point, they're slow enough that they get stuck in this laser field. So we turn off the laser cooling beams, and let's zoom in on the optical lattice. Now we can finally see that standing wave pattern, regions of bright and dark, bright shown in red and the dark and the lack of red. And there's a few atoms that are stuck in there. Now we send a pulse of light down the axis of that optical lattice. This is a special pulse of light. This is what we call our clock laser. This is the laser that actually excites the electron to get the ticking, if you will, of the atomic clock going. And as we do so, some of those atoms get excited, and then we just need to ask the question, did you get excited? Were we at the right frequency? And so we turn on these blue lasers again, which basically give us a way to ask the atoms if they've been excited. If they haven't been excited, it turns out they absorb these blue lasers, and then they re-radiate, they fluoresce that light, and we can detect that on a sensor here, a photomultiplier tube. And so that is effectively our clock signal. It tells us how to adjust the laser frequency in order to synchronize it with the atoms. And then we send that to this frequency comb, and we've got ourselves an optical clock, in this case, an optical lattice clock. Okay, so what makes the optical lattice clock special, and why is it capable of making measurements that are so good? Well, I wanted to go over the salient details of this. The first and foremost is it has this high energy electronic transition compared to a conventional atomic clock. This is what I was saying before, that if this excited state is at higher energy, then we need an optical photon, not a microwave photon, in order to excite the electron. And that means much higher frequency. That means we divide time in much finer detail. As well, the atom spends a long time. Once we excite it up there, it'll hang out there for a long time. In this case, we're talking about many seconds, and on the atomic time scale, that's like infinity. And so the atom's the electron's kind of hanging out there, and it turns out that this means that we can sense the laser frequency very well. And this goes back to the Heisenberg uncertainty principle or Fourier theory, depending on how you like to think about it, that anytime you make a measurement that lasts a long time in the time domain corresponds to a very precise measurement, a very high resolution measurement in the frequency domain. And so what that means is when we look in the frequency, we say, how can we excite this atom? This is the amount of excitation that the atom experiences versus the frequency of the laser. This little bump here gets narrower and narrower the longer time we spend looking at the atoms. And that's also, it sounds like from the minutes, what Bill was talking about last week. Okay, so the reason this is important is if it spent less time up there, then rather than having this, we'd have something like that or much worse than that. And so we wouldn't be able to discriminate the frequencies quite as well. Okay, another reason why the optical lattice clock is so special is because there's a lot of atoms there. That's a relative term. Actually, there's usually in one of these lattice clocks, there's between 1,000 and 1,000,000 atoms. According to the normal worldwide experience, that's nothing, but for comparable type of optical clocks, that's actually a lot of atoms. And this turns out to be important. These can sometimes be trapped in a multidimensional lattice like this or a one-dimensional lattice. But this is the reason that's important. So we have all these atoms, and we're making measurements in all these atoms by watching them fluoresce photons onto this sensor. And again, what we're trying to do is we're trying to excite that atom from its ground state up to its excited state. We know from quantum mechanics that actually what really happens is most of the time that we're doing this process, the atom actually sits in a superposition state. It's actually both in the ground state and the excited state. And when we ask the atoms, which state are you in? Did you get excited or are you still in the ground state? That what ends up happening is it collapses this superposition into an answer which is one or the other. And random probability dictates which answer we get based upon the amplitudes of the wave function for those different states. So there's some randomness quantum mechanics gives us associated with what answer the atom gives us. Are you in the ground state or the excited state? This is called quantum projection noise. And ultimately, this is what fundamentally limits the performance of an atomic clock. If you have tons of atoms around, then you get to ask this question to every atom, and they all give you random answers, but you get to average out their randomness, and they give you a more precise answer together than any one would give by themselves. Okay, finally, one other important detail of the optical lattice clock is the ability to control the Doppler effect. When I first became familiar with the Doppler effect, it was I think, looking in a textbook at a picture of a train. The train is blowing the horn, it's approaching you, and you hear a certain tone of the train horn, and as it passes you, that frequency seems to change, the tone change. It kind of goes from high frequency down to low frequency, and this is known as the Doppler effect. It's just because as the train approaches you, its own velocity makes the frequency seem like it's actually higher, and then as it's going away from you, it makes it seem like it's lower. So whether we know it or not, we experience this in everyday life quite a bit, and the atoms sure experience it. When we're shining that laser beam on them, trying to excite them, that atom is moving around at some level, and so the frequency of that light gets Doppler shifted. And so we have to take that into account, and that could totally mess up our measurements. What that would mean is that this atomic excitation, this resonance that we're trying to hit, it could get shifted over because of this Doppler effect. So we need to make sure that's really well controlled. That means we don't want our atoms moving around. So how do we do that? Well, the first thing we do is we laser cool them. Cooling the atoms means we move them from moving around, we change them from moving around a lot to very little. So that helps out a lot. That reduces the Doppler effect quite a bit because they're not moving as much. But that's not enough still. Even at a millionth of a degree above absolute zero, the Doppler effect on these atoms is huge compared to what atomic clocks are used to seeing. And so we need to do something more, and that's where this optical lattice comes into play. It basically traps them. What I've tried to draw here is like a bowl, if you will. Think of the atom as a little marble, and it's stuck inside this bowl. And this is just one little region of bright intensity of that laser beam. It's stuck in there. But because the atom is a quantum particle, its motion in this little bowl is actually quantized. It can't move around any way it wants to. It can only move in energy states corresponding to these red lines. Anyways, the important thing is that on average, this atom isn't moving around. It might be wiggling around in there, but it's not on a long time scale. It's not going anywhere. So that means the Doppler shift is basically controlled. And so together, we can eliminate this effect. And so that's really useful for the clock. But there's a very big caveat with that. We absolutely need that optical lattice to hold on to the atoms so that the Doppler effect doesn't kill our measurement. But the problem is that optical lattice, the way it holds on to the atoms is basically the electric field interacts with the electrons and it distorts the cloud of the electron around the atom. And as it distorts it, it actually changes the energy of the bound states of the electron to the nucleus. And this is bad for us because that's effectively what we're trying to measure. We're trying to measure the energy difference corresponding to Planck's constant times the frequency of light that excites the electron between those states. And imagine that the unperturbed, what nature gives us are these black lines, and then we put on this bright laser field, and these dashed lines, it changes. And now when we try to measure the frequency, it's not the actual frequency that the electron would normally experience. It's being changed by this laser field, this very intense laser field. What's worse is that the amount that this changes will change depending upon how strong of a laser field we're using. If we use a really intense laser, it's a really big effect. So this is a problem for us. And so the solution is by operating the lattice at a optical wavelength, which is known as the magic wavelength. So we like to use magical techniques even in this kind of research. And the idea is simple. What if there's a way that optical lattice, when it distorts that electron cloud, it distorts it the same for an electron in the ground state and then one in the excited state. Exactly the same. All we're really measuring is the energy or frequency between those states. So if they move by the same amount, it's as if they didn't move at all for our comparative measurement, measuring the difference between those. So this is operation at the so-called magic wavelength. And it works pretty well. Okay, putting that all together, we can identify some atoms that are actually able to realize all of those characteristics we just talked about. It turns out that they're mostly atoms that have two valence electrons that are in this group 2 column. There's 2A, 2B, and then there's our little friend ytterbium that we actually use, which, like these other guys, has two valence electrons. And it just turns out that because it has two valence electrons, it has some special properties which means that we can do all the stuff we just talked about. In particular, in their kind of asterisk, strontium, mercury, and ytterbium are kind of the most popular choices right now for this type of clock. Okay, so putting it together, we have high energy electronic state. We can check that box. We've got that. Long-lived excited state, which means it has a very narrow band resonance. We've got that. Large atom number ensemble, so that we can average away this so-called quantum projection noise. We got that. The ability to control the Doppler effect with this magic wavelength lattice. Okay, so we've got everything we need to. Here's the same picture of that same optical lattice experiment that I showed you, but now we've turned off the lights and we've played some tricks with the exposure so that you can see the laser beams a little bit more. This is the optical lattice laser that's holding the atoms. This yellow laser right here is our special clock laser that actually excites the atoms and starts the ticking. This kind of purpley blue and that green laser are what actually cool the atoms down for us. Okay, just by way of my own information, what time should we be finishing here? Okay, so maybe give me a little guidance because I'm worried that I'm going to go too far off. So, okay. So the question is, how good can these clocks be? Well, to kind of really think about the right way to characterize that, I wanted to start with a simple example. We know that if we flip a coin, there's 50% chance we get heads, 50% chance we get tails. But let's pretend that someone asked us to prove that to them. And so we had to do an experiment. We get out our quarter and we start flipping it. And of course, it's, in principle, a random process. It could be that the first couple times we keep getting heads. So if you asked me after 3 flips, what's the probability? I could give you the wrong answer. I don't have a very good answer for you. But if you let me flip it 10 times, 100 times, 1,000 times, I'm going to start giving you a really good answer. And we could kind of plot that here as my statistical uncertainty with how well I can tell you the average really improves the number of times I toss that coin. This is just kind of straightforward statistics, averaging away of a random process. Well, for a clock, what really matters for making a good measurement of time is the fundamental limit to how good we can measure time is, yeah, that pendulum that's swinging back and forth, how stable is the oscillation frequency of that? Does it always oscillate at exactly the same rate, or sometimes does it slow down or speed up based upon, I don't know, the temperature or the humidity, or if someone bumps into it? If it changes for any reason, then that means we're not going to be able to measure time very well because our time base is changing. So for a clock, you can characterize what typically we call as the clock instability. How unstable is the clock as a function of measurement time? And same kind of thing, if I measure longer, that means I've made more measurements, and in principle, I'm able to average away the noise that creates instabilities in the clock system. And so, as a general rule, if I'm lucky, I'm going to be able to actually improve my measurement instability, which is almost identical to the precision that I can measure time with. I'm going to improve that over time. And there's a formal name for this type. It's a two-sample statistical tool called the Allen deviation. So I'm going to show you a couple plots with that, but I wanted to describe roughly what it is. So here's the experiment. We have 2 optical lattice clocks based upon ytterbium. We need 2 of them because we think that one of them is so darn good that we cannot measure it against anything else because it's better than anything else. And so we need 2 of them so that we can measure against each other, and we might be able to see how good they are. So there's 2 of them. There's some shared properties here. This is basically just the laser system that starts out with. But ultimately, the laser light, which starts here, it goes to one optical lattice clock system and then to another optical lattice clock system. And there are some various transducers that we use to tune the laser light to the right frequency and so forth. That's not terribly important. We make measurements then comparing these 2 systems, and this is what we see. This is, again, is the measurement of how unstable the clock is as a function of our measurement time. And we are fortunate it has a noise process that does average down. If we wait longer, it gets better. And eventually, if we wait long enough, in this case for about 25,000 seconds, I think that's like 7 hours, we can actually get a stability corresponding to a precision of 1 part in 10 to the 18. So that corresponds to the measurement of 1 second over the age of the universe, 14 billion years. This is now an exciting number for us. This is what, when we're thinking about the gravitational redshift, this is 1 centimeter of elevation change, what this clock can do. Under this data, which are these red dots, is a blue line, and this is our best estimate of what we think the clock should be operating at, based upon, first, this so-called quantum projection noise, this quantum noise that we have to average through, and another important effect called aliasing that I'll describe in just a minute. And so, actually, the performance of the clock mirrors pretty well what we think it should be. I'll mention this is a logarithmic scale on both axes. So, we start out at short times measuring a part in 10 to the 16, but eventually at longer times we get about 2 orders of magnitude gain down to the part in 10 to the 18. Okay, so we get excited about that level of performance because it really opens the door for these new potential measurement applications. To just give some perspective, here's some of these other fancy atomic clocks that I've been describing. This hydrogen maser that actually is commercially available but costs a good fraction of $1 million. That's its instability, the black line. A so-called cesium fountain, which is basically the most sophisticated cesium clock. And remember, cesium is the definition of the SI unit of the second and the hertz. So cesium clocks are very good. And this is the best of those. That could be as good as this red line. Then when you start moving to these so-called optical clocks that are operating at much higher frequencies, there's one type of optical clock using a single trapped ion. That's this green line. And finally, here's this new type of clock, the ytterbium lattice clock that's coming in. So again, the logarithmic scaling. So there's basically an order of magnitude improvement with each one. And because the way it averages down, if you wanted to get to the same performance that blue dot is there with that green line, it would take square the number of times. So in other words, there's 1 order of magnitude difference, but it would take 2 orders of magnitude to average down to get there. So kind of a substantial improvement. But even then, we're not at the limit of these systems. We can do better. There was this aliasing noise I was talking about. So this is a technical noise that we had to work through in the last couple of years. Probably the most obvious example of aliasing, I think, is when we look at a car commercial and we see the car driving by, and every once in a while it seems like those wheels are turning backwards, right? And that's simply because the speed, the revolutions of those wheels is slightly slower than the frame rate of the camera taking the pictures. And so kind of like as if we were blinking our eyes real quick, we would be looking at it each time where it seems like it's going backwards, and it's only because we're just looking stroboscopically at what's going on. So this is aliasing, the idea that there's some process happening at a higher frequency that because we sample it at a particular frequency, it appears to happen at a much lower frequency. In this case, it could even have a negative sign, going as if the wheels are going backwards. Same kind of thing happens in atomic clocks, it turns out. So I take my laser and I shine it on the atoms. Unfortunately, I'm not shining it on the atoms all the time. I've got to spend time in this clock laser cooling the atoms. I've got to spend time measuring when I ask the atoms, did you get excited or not? That all takes time, which means I can only spend part of the time shining this clock laser on them to try to measure the ticking rate of the atoms. It's kind of like this. If I describe our experimental cycle, we spend some time actually making a measurement of the atomic ticking. I'll call that probing the clock. But then we spend other time doing readout or preparation. So anyways, we are only making meaningful measurements every once in a while. And so that means part of the time we're not making meaningful measurements. And this is kind of like a digital sampling of what is the laser frequency. And unfortunately, this laser has some noise at all kinds of frequencies, and we can downsample that noise and detect it at a frequency that it doesn't actually exist at. So this is an aliasing problem. It's actually called the Dick effect, named after a physicist at the Jet Propulsion Lab of NASA, John Dick, who first illuminated this phenomenon for atomic clocks. Well, there's a couple solutions for this. And this isn't such a big deal, and for time I'll maybe glaze over this a little bit. The idea is if my laser that excites the atoms doesn't have a lot of noise on it, then I don't care if it aliases or not, because there's not noise to really get alias down into my measurement. So it's not a problem. So there are ways of making a very good, a very quiet laser, and by that I mean that it has a very stable output frequency. And it's called cavity stabilization. It's almost a whole field unto itself, where we take a laser and then we shine it on a so-called optical cavity. It's just 2 mirrors. It turns out that the laser light will only go inside those 2 mirrors if the wavelength of light it actually meets a resonant condition, that the distance between those 2 mirrors is an integer multiple of the half wavelength. And so you can basically lock the wavelength of this laser to the spacing between those mirrors. And by so doing, you can make the laser wavelength and thus its frequency much more stable than it would be otherwise. So this is a picture of such an optical cavity, or at least a graphical representation. There's a mirror there, and there's a mirror on the backside, and there's some low expansion glass. And believe it or not, it's possible using these techniques to keep the average length between these mirrors more stable than the radius of the nucleus of the atom. It's a modern marvel of physics and engineering, but it can be done, and it can mean that you can make this laser, have a line width which is like less than a hertz and be very frequency stable. So we've done things like that to try to make our lasers better, or we've also done this more recent trick where we actually have 2 of these atomic systems, and we operate them so that at any given time, the laser is always exciting the atoms. There's never a time when it's not. And in this way, we can effectively eliminate this aliasing process because we're not sampling with this dead time that separates the measurements. So this is another tool that we've used. And by combining some of those techniques, we've been able to make some improvements. And this is actually data that we only took a week and a half ago, so this is not even published yet, where we've been able to make that same kind of measurement. In this case, it's about 1.5 × 10⁻18. Before, it took us 7 hours. Now we can do it in about 5,000 seconds, which, what's that? That's like, so 10 minutes, 50, an hour or so? Yeah, thank you, in an hour, yeah. So we're doing pretty good there now. This is starting to get interesting for us because now, this is the name of the game, is can we make these useful measurements, these really exciting measurements on a useful time scale? Okay, so it just keeps getting better, and I'll say even now, we're not at the limit. These systems are capable of more. So as I kind of go towards the end here, there's an important aspect that I haven't talked about. I've mostly been talking about right now, how stable are these clocks, which determines how precisely we can measure time. But there's a whole other concept here, which is the accuracy. And what I mean by that is, let's pretend that in this pendulum clock, that pendulum is swinging back and forth, and it never changes its oscillation frequency. It's always the same. We think it's oscillating once a second, but it's actually oscillating once every 0.9 seconds. So it's not changing. It's incredibly stable. We could make, in principle, very precise measurements with it, but we'd be wrong because we think we know the time base, but we don't know the time base. And this is accuracy for a timepiece. In our case, for the atom, what we mostly worry about is when we are trying to measure the ticking rate of the atom, we're wondering, is this the ticking rate that Mother Nature gave it? Is this really what the universe has provided for us? In other words, we want our atoms to be 100% natural. We don't want anything else going on. When in reality, we know in the real world, there are magnetic fields, there's electric fields, there's light fields, there's other atoms bonking into these atoms, all of these things that ultimately change the electronic behavior of the atom, and thus will change the ticking rate of the atom. So the name of the game for accuracy is trying to understand all of these effects that go on and controlling them and characterizing how big of a problem they are. So what we do is stuff like this. We make a so-called uncertainty budget where we make a list of everything that we can think of that would mess up the ticking rate of this atom. And then we try to either devise a model based on first principles to compute how large of an effect this is, or more preferably, try to devise an experiment in order to measure this influence and characterize how well are we able to measure the true natural oscillation frequency of this atom. And so this is each effect and how well we can do it. And this is actually our uncertainty budget that we work on these every couple of years and try to improve them. And I have a question mark here as our total uncertainty because we're not quite done. There's a couple of effects that we're working on right now in the lab. And we're pretty close to being done, and the hope is that the total uncertainty at this point will be about 1 × 10⁻⁸, which again corresponds to this kind of 1 second over the lifetime of the universe. Just as an example, things that we worry about, the black body environment. So this is a picture of a train engine. It imaged at 10 microns where you can see the heat coming from the engine. In our laboratory, everything's at room temperature, even though these atoms are at just above absolute zero. And all of that room temperature stuff, it's actually bathing the atoms in infrared radiation. And that radiation, it distorts the electron cloud just like other stuff does, and that causes a problem for us. So we have to really carefully characterize that. Again, for time, maybe I'll jump through some of this. There's another thing that we think about a lot, which is tunneling. These atoms are quantum particles. They're not just stuck inside this potential. Quantum mechanics actually tell us that atoms are not particles, but they're waves too. And so this wave might extend more than this little region here. It might extend out to this region. And that means that if we measure where the atom is, occasionally it might pop up over there. And this is known as quantum tunneling. So in these quantized states of motion that the atom might occupy, sometimes it'll jump over there. And this creates for us a Doppler shift because the atom's moving around. It's no longer trapped. And so we have to worry about things like this. Okay, so at the end of the day, we put together these uncertainty budgets. And we work really hard to try to make sure that this is a small uncertainty, but that we've carefully thought about everything we could. Sometimes, though, you ask yourself the question, what if I forgot something? What if I left something out? At the end of the day, nothing can replace measurements between these clocks. which finally tell us how good are these systems. We need to compare them against each other and say, yep, these two systems that are otherwise identical agree at 1 part in 10 to the 18, and therefore I really trust this. So comparisons of these clocks becomes very important. As a result of this, and because this is a very interesting technology, there's a lot of groups around the world that are working on optical lattice clocks. I've tried to highlight all the ones that I'm aware of at this point. This really, truly is an international effort where we benefit greatly with collaboration. Different groups will study different systematic effects and will learn things from their results that get published in the literature, and together we're really evolving as an international community to make these clocks better. And the dream is that eventually we'll be able to link these up and compare them as well. So there's a number of efforts currently underway where we might compare them. Am I still okay in time? Okay, good. 5 more minutes, I promise. So one exciting thing that's coming online soon is called the ACES space mission, Atomic Clock Ensemble in Space. So this has been a project that's been in the works for a long time and is currently led by the European Space Agency. And the idea is that they will actually put an atomic clock, this little ACES payload, on the International Space Station. It's actually scheduled to fly later this year. We'll see if it actually happens. It's been moved back a lot. But the idea is there is something nearly very similar to a cesium fountain clock, which is a very good traditional atomic clock. It's about the best that there is, as well as a hydrogen maser. So this actually means this will be quite useful for making measurements of gravity like the gravitational redshift. But furthermore, there's a communication system that, together with this ground terminal, allows us to compare clocks that are located on the ground by an uplink to the International Space Station. And because that thing is orbiting around the Earth every, I can't remember, 90 minutes or so, it allows us to actually compare our clocks, let's say in Boulder, Colorado, with those at national metrology institutes around the world. And it can do so at a level that actually far exceeds what's possible with current satellite time transfer. So we have the expectation that we're going to be able to compare clocks eventually at a part in 10 to the 17 on an international level. There's even a better approach at comparing these clocks based upon optical fiber networks. It turns out that the noise that you add in a timing signal through the atmosphere can be quite bad, but an optical fiber is a much more controlled environment. So if you send light down an optical fiber, its frequency is going to change a little bit due to a number of processes, but you can control that in a very easy way, such that when you deliver your signal, it arrives at the destination nearly as pure as it started before you sent it down the optical fiber. So right now in Europe, for example, there's a so-called NEAT-FT optical clock network where they're linking up all kinds of universities and metrology institutes around Europe that are developing a number of clocks, including these advanced optical clocks. And this will be actually really exciting too. So there's ongoing work like this as well in the United States and in Asia. But probably the most prominent one right now is in Europe, simply because they happen to have a lot of countries in one continent where it kind of makes sense to do this. Okay. Oh, it turns out that the power was not plugged in. So we'll see. That might have been it, folks. Well, I think this guy shut down. Apparently, and apparently the time of duration is about an hour. I'll tell you what, so there was just kind of a funny little joke there at the end, but why don't we do the question and answer period, and then I might pull it up here for the last minute. Is that good? Okay, well, good. Well, thank you very much for your attention.
Your name, whether you're a member of PSW or you're not, a guest, if you're a guest or a member of PSW, and ask a question.
I'm Bob Hershey. I'm a member. Your choice of material in this was ytterbium. Is that the ultimate choice, or there might be some material that does even better?
Yeah, so it's exactly that question which motivates different type of atomic systems to be used in the first place. Based upon theory, we can make best guesses as to which might be the ultimate systems, and this usually limits the field down to a handful. But beyond that, only experiment can really tell us. And so it's fortunate that around the world, different systems are being developed, and that's really a big question that we're trying to answer right now, is which one is the best, and we don't know. A kind of side benefit of this is a lot of these fundamental science measurements require different types of clocks to be compared. If we all developed the same one right now because we knew that was going to be the best one, there'd be a lot of really interesting measurements that we simply could not make because we'd be stuck with the same atom.
We have one question in the back there, and then we'll come back to the front, and then we'll go back to the back.
Thanks.
So-
My name is Lynn Fellman. I'm a member. Thank you, Dr. Ludlow. That was a very, very good presentation. So, fundamental constant can vary. It sort of counters itself out or something, crosses itself out. Well, you know what I'm trying to say.
It's an oxymoron, yeah.
Yeah, that's the word. All right.
Absolutely.
I love that concept. Could you just say some more about it? It's an open-ended question.
Yeah, and perhaps it's as much philosophical as it is anything else. So when I first heard the concept of this, the speaker at that time basically answered a similar question to, well, why not? Why not have them change? We're accustomed, maybe we've been taught that they are the same, but why do we expect that they ought to remain the same? We know that the universe has changed quite a bit since the Big Bang, and so perhaps it's natural to expect that some of these constants of nature have changed as well. It's actually interesting when you start thinking about how much they change by. For example, this fine structure constant, which ultimately can be expressed in terms of like the electron charge and the speed of light, it doesn't have to change by much before life as we know it would cease to exist. Chemical bonds wouldn't work, and the atoms just would not behave in the same way. So there's kind of a sweet spot for life that ultimately these fundamental constants would have a value that sustains life. In any case, it's an interesting idea. I don't know if I can illuminate it too much. I do think it is reasonable to say that there's been a lot of change in the universe, and so maybe it could actually vary. And that's why I actually like that these experiments are complementing these astrophysical measurements where they're looking back in history much longer, where maybe there's a higher chance that it's changing at a rate that we could detect. Anyways, I didn't completely answer your question, but hopefully talk to it a little bit.
Hi, Michael. And so you were talking about comparing clocks, and this raises kind of two related questions. One is comparing a clock the same thing as synchronizing the clock? And two, if you're comparing the clock and you're sending a light beam between one clock and another, I can't imagine that the light beam is oscillating as fast as your clock is oscillating. So how are you able to compare something that's oscillating much, much faster than you can oscillate the light beam?
Yeah, could you say again the first part of that?
So it is comparing two clocks the same thing as
Yes.
synchronizing them?
Yeah, so it's not the same. In order to synchronize them, you effectively need to make a measurement which is at least equivalent to comparing them, but it's more than that. I suppose you could compare two clocks that are ticking at different rates. You could make measurements on them, and they wouldn't be synchronized per se, but you could still measure that. Synchronizing is going one step further and then forcing one of them to oscillate at the same rate as the other. Technically, they call that syntonization, where they're operating at the same frequencies. In any case, so that would require some additional steps. That would require you to actually manipulate the light wave some rather than just measure it. So that light wave, the primary purpose of the atomic system, which oscillates at that frequency, by responding to the light, is you're effectively trying to synchronize the light field with the electron, the electron wave function motion in the atom. And so you are actually synchronizing in that regard. So I think that was with regard to your second question. that you actually do get them to operate at the same rate. And to the extent that they don't do that, you've built a bad clock. Then at that point, it's not doing quite what you want it to.
Question in the back there, and then the man in the blue shirt after.
I'm Kirby Runyon. I am a member of the society. I was just curious, in your laboratory setup, you've got lasers going through the air, which has a slightly slower speed of light than through vacuum. And I'm wondering how that's taken into account in the experiment.
Yeah, that's a really a good point. And unfortunately for time, I didn't really get the chance to talk about this. So anytime we send the light anywhere, it typically gets messed up a little bit. Because of, let's say, the index of refraction and variations of the index of refraction with air currents and so forth, that can compromise the performance. So when we made some of these measurements that I showed here, where we're comparing the stability of the clock and getting at a part in 10 to the 18 in just a few thousand seconds, in order to do that, we had to use a technique which is called a phase noise cancellation. And basically what that is we use an interferometer to sense how much the optical phase might change as it propagates through the air. And we detect that by basically taking the laser beam and then just reflecting just a little bit backwards. And then we create a Michelson interferometer that it compares the phase of that long path that could have a lot of noise to a little reference arm path, which has a very stable phase. And this gives us a way to detect whether or not the light frequency or phase has changed. And then we make that measurement, and then we adjust for any noise which has been created by effectively writing the anti-noise of that noise onto a transducer called an acousto-optic modulator. And this allows us to compensate for this effect. In fact, this is actually also what's done in that fiber network I showed you. It's even worse in optical fiber than in air, because that glass medium has a higher index of refraction. And sound waves and thermal drifts and mechanical motion changes the index of refraction of that glass in the optical fiber, and it makes this problem even worse. But the same type of techniques can be used to measure the amount of noise, and then we can write the anti-noise on that and compensate for it.
Thank you. I'm Jim McCormick. I'm a guest, and thanks for making the trip out here. Can you hear me okay? My question is that underlying this appears to be a feedback loop on your fundamental frequency, and you're measuring it with this optical comb filter. That implies to me that over this 7-hour period that you're sampling, you're bumping up against the stops. You're getting a little bit out of tune and then back in. And how do you compensate for that? Is there an ensemble of atoms that are generally stable and then a few canaries are kind of drifting off to let you know? Or how do you deal with that?
I'm not sure I completely understood. Could you restate that again?
Sure. So there's a frequency that you're controlling, and the way you're controlling it is by monitoring the reflectivity of your lasers, because when the atoms aren't quite in the right frequency, you're getting a little bit of scintillation. So when you see that scintillation, I assumed you're using that as a feedback loop to modulate your frequency to keep it right on track. Right. So in order to get that signal to close the loop, you kind of have to get a little bit of out of sync.
Right, okay,
Right.
Good point. Yeah, so that's entirely true. You're exactly right. We use a feedback mechanism in order to hold the laser frequency in resonance with the atoms. And it takes us about half a second to do that whole experimental cycle I measured, where we cool the atoms and we measure them. And so we only get to look at the atoms twice a second. And that means the bandwidth for that feedback loop is not very high. It's Hertz level. And so as a consequence of that, definitely the laser can, on that half-second time scale, can naturally wander around. And the important thing is that it does wander around and it gets off resonance slightly, but on average, it's locked to the mean position, to exactly on resonance with the atom. So that even if it wanders off a little bit, that wandering is actually kind of what's going on with this little bump right here. But importantly, once within the bandwidth of our feedback loop, once we've actually tracked the atomic transition well, then we do start averaging down with noise intrinsic to the atomic system, and that small wander doesn't affect these longer timescales that we care about.
Question right there. Yeah, you? Yeah.
Upendra Shevde, I'm a guest. Thank you. It's a very interesting talk. My question was, the first part was a clarification. So if I understand correctly, the output of the clock is a laser beam, the clock laser beam, whose frequency is known theoretically, right? So then the question is, how do you generate lasers that are basically that narrow? And the second thing is, how do you consume the laser? Like, what are the electronics behind it and so on?
Okay.
Could you repeat the question?
So the first question, as I understood it, was regarding, actually, now I'm remembering the second and not the first already.
The first one was just, is it correct that the frequency, the theoretically known frequency of the clock laser is the output of this experiment? That is the one that's really the clock.
Okay, and with regards to that, you also asked, related to that, how do you make that super kind of stable laser frequency? Okay, so first of all, based upon theory, we approximately know the right frequency of the transition. It turns out for something like hydrogen, you can calculate that very well because it's a simple enough system to calculate using very sophisticated techniques. But for most real atoms, and especially like ytterbium that has tons of electrons, it's an extremely difficult task to try to calculate based upon kind of ab initio theory what the transition frequency should be. So they can do that, but they can't do that nearly, it's many, many orders of magnitude below what we learn based upon experiment. So really our best way to try to learn what that frequency is by going through that careful study I was mentioning where we try to think of every effect, measure it and control it, and then eventually we extrapolate what the natural oscillation frequency is. And then we either have to measure it again to make sure we got the right answer using a somewhat different situation, or wait for another group to measure it and say, oh, we got the same answer. And that's effectively how we kind of arrive at an agreement. And this is actually an important process. Right now, ytterbium and the ytterbium lattice clock and the strontium lattice clock have been accepted by the International Organization for Time Standards, the Bureau of Weights and Measures, International Bureau of Weights and Measures. They have been accepted as so-called secondary representations of the SI second, which means you can use them to define time and frequency. However, the primary definition is still cesium. And the way that they got accepted as secondary references is because, one, they're really good, but because multiple groups have measured them and they get the same answer. In the cases where different groups around the world make different measurements, they say, well, we've got some things to figure out before we rely upon this as a standard. To make that laser super stable, that was kind of what I was showing before, and I wish I could have spent a little bit more time on that, this so-called optical cavity laser stabilization. And let me just jump to that slide real quick here. Yes, this one right here. And again, so that idea is that it turns out that we can make the spacing between a macroscopic object very stable. In this case, we'll use this so-called ultra-low expansion glass. It has a coefficient of thermal expansion that's about 1 million times smaller than normal materials like metal or something. And so we put mirrors on either side of this kind of low expansion spacer, and it holds that the spacing between those mirrors very stable. And then we stick it in a vacuum system, and we temperature control it, and we do everything we can to keep nature from shaking or perturbing this thing. And then we shine a laser onto it, and only when the laser frequency is just right are we able to inject light into this cavity. And it's called a cavity basically because this is a high reflectivity mirror. Normally it just reflects it back. But when you meet this resonant condition, when an integer multiple of half wavelengths can fit inside there, a little bit of light leaks up in there, and then you get constructive interference, and it builds up the intensity very high. And only when you meet that resonant condition are you actually able to get light out of the cavity. So when you monitor, let's say, light coming out of the cavity, I guess I've drawn it backwards here, I'm sorry. The only way you get light out of the cavity, if you monitor that, you can hold the laser frequency in resonance with the cavity, and that effectively gives us a tool to make a normal laser, which might have a very large spectral bandwidth, megahertz or more, and make it much, much more stable with a frequency spectrum that would be like 1 hertz. This laser right here actually has a frequency spectrum of about 100 millihertz or so. And so that's important for, we need that for the atoms, because even though normally we're used to thinking of lasers as coherent sources of light, compared to these atomic systems, laser light is incredibly incoherent. And we need to work very hard to make it more coherent first by pre-stabilizing it, and then it becomes useful to actually excite the atoms. So I hope I've answered that question. What was your last question now?
How do you consume the laser? Like, how do you convert the frequency of the laser then into sort of electronic
Okay.
clocks?
So, and that depends upon the type of laser. We use a lot of solid-state diode lasers. We also use some lasers based upon photonic processes and crystals. And we have different ways to change the frequency. In a diode laser, there's basically just electric current which can converted to light. It's maybe not so different from like an LED. And in that case, by adjusting the amount of current, we can actually change the frequency somewhat of the light. This gives us a handle to change it. But there's also another tool that we use in addition to the laser itself to change the frequency. And I didn't mention it here, but that's this so-called acousto-optic modulator. These are cool little devices that basically the light goes into a crystal, and then you hit that crystal with an acoustic wave. And it actually is able to diffract the photon with the energy of the acoustic wave. And in so doing, it actually shifts the laser frequency by the frequency of the acoustic wave. So that these are very high frequency acoustic waves in the megahertz range. So anyways, this gives us a way to change the laser light frequency at the megahertz level. And so, and we can tune that very finely if we want to adjust exactly to the atomic transition. And that's what we most often use.
Any other questions? Last question. Carl. Wait for the microphone.
Carl Merrill, member of the society. Given that you're going to have arrays of these all over the Earth, what use is this going to be for detecting perturbations in space-time? And what's your prediction for that?
Yeah, so that's a really interesting question. And this is something that I would say our community has only started thinking about. There have been some proposals in the last couple of years to try to compete with other gravitational wave observatories like LIGO or this space-based LISA program, where they're trying to think, how can you use in atomic systems? And the most popular choice right now is to use a so-called atom interferometer that they could be separated over long baselines, and they could actually, these devices are useful for measuring gravitational effects, and they could be used potentially for detecting gravitational wave. But more recently, as early as I think the last 6 months, there's been proposals saying, well, actually maybe these atomic clocks could be equally good at detecting this. And I want to say at this point in time, we haven't really wrinkled out the details. Some initial numbers that some people have put pen to paper shown that this could, in principle, a global network of these type of clocks might be able to perform, at the level of LISA, although sensitive to maybe different frequencies of gravitational waves. I don't know the details yet, but this is something we're starting to think about, and I hope in the next few years this is an area we might be able to contribute to. So, not a completely satisfactory answer, but definitely it's something that we're starting to think about.
Well, thank you very much.
Do I have a chance for the last slide?
In appreciation for your coming here and giving this talk, I'd like to present you with this framed and signed copy of the announcement of your talk on behalf of the General Committee and all the members of the Society.
Thank you very much. Okay, so in the last minute, I just wanted to show this kind of funny circumstance here. So when we first demonstrated this 1 part in 10 to the 18, showing that nominally precision at 1 second of the age of the universe, it picked up a little bit of media, and there were some funny things that came out of that. I'm not sure that it's funny to see the other side of things, and it makes me want to never trust a media report because it's easy to get things wrong. So it turns out in 2013, TimeLife.com ranked the ytterbium clock as looks like the 17th invention, best invention of the year 2013. We were pretty excited about that. I mean, I've heard of Time Life before. But then as we kept digging deeper, we realized that the cronut, which is a cross between the croissant and the donut, ranked number 6. And so we felt like we really needed to up our game next time around, see if we can outperform the pastry. After this happened, though, some of this media attention, one of the postdocs on the experiment was monitoring Twitter and found that actually the actor Steve Martin made a comment based upon some of this work. Just got word on a new iPhone feature, an atomic clock based on ytterbium atoms that keeps perfect time for the age of the universe. Now, just in case there's a lot of age groups here. Steve Martin's been around for a long time. Depending on how old you are, you might think of Steve Martin as that guy, or maybe that guy. I usually think of him as that guy right there. So it sounded encouraging, but then the Twitter feed kept on going, and his friend Arnold Feather was not so impressed. He labeled the clock as an overrated eyesore compared to his house clock, which is the moo cow clock, claiming superior accuracy. So our feelings were hurt a little bit, but nevertheless, we talked to the NIST Public Relations Department. We were able to get an official response on Twitter for NIST, inviting Steve to stop by the lab and check out the prototype. Hasn't happened yet, but if you're in the audience, Steve, the invitation is still open. So anyways, a couple of funny anecdotes from that experience. Again, thanks for your attention.
I have to do a little bit. So before we adjourn to the social hour, a few closing items. PSW depends on an enthusiastic, active, and capable membership. Without these, no PSW, and no free lectures like this one. Really. So please join if you're not a member. And if you are a member, please see a member of the General Committee about getting involved and helping out with staging these lectures. You can apply for membership on the PSW website, www.pswscience.org. It's easy. Just go to the website, look for the application form, click on the button, and fill it out. And then pay the fee, and you'll become a member. If you're a meetup member, and how many of you are meetup members? That doesn't mean you're a member of PSW. So if you're not already joined PSW, please do. We love having meetup people. In particular, we love having meetup people who join PSW. If you have questions about membership, please see our membership chairman, James Heelan, who may be around somewhere. There he is. Or corresponding secretary, Robin Taylor, or myself, and we'll be happy to answer any questions you have. PSW is a nonprofit educational organization, tax exempt under Section 501c3 of the Internal Revenue Code. Contributions generally are tax deductible. Our next lecture will be the 2,358th, and it will be on February 19th in this room, and the speaker will be Robert Hazen, staff scientist at the Carnegie Institute for Science and Robinson Professor of Earth Sciences at George Mason University. His topic will be chance versus necessity in mineral evolution, a new approach to an ancient subject. But I could condense that to tell you that he has some very interesting things to say about the environment in which life probably originated, and that has to do with mud, which interestingly relates to pre-biblical stories of the origin of life. But that's a discussion for the social hour. So the spring schedule has been posted to the website. Again, www.pswscience.org. And I'll be filling in the 2 missing lectures in the next week or so. We're going to adjourn to the social hour, which ends at 10:30. After that, a group of PSW members and their guests will go across the street to the lounge formerly known as the Jockey Club and now known as the Fairfax Lounge to continue the discussion. If you want to join us, please see our membership chairman, James Heelan, or our corresponding secretary, Robin Taylor, or myself, and we'll be happy to show you how to get there. So with that, I will accept a motion for adjournment of the meeting to the social hour, which will end promptly at 10:30. Thank you, Bob. A second? All in favor? All opposed? The meeting is adjourned.